You've probably heard that 98% of your body is water. Well, that number is actually incorrect. In fact, on average, humans are closer to 70% water. But that's beside the point. Bones and teeth contain very little water and are incredibly rigid. Why? What is it that makes them so hard? The answer is minerals. A mineral called apatite, to be exact, and note the spelling, A-P-A-T-I-T-E. There are many different types of apatite minerals. In fact, we say that there is an apatite mineral family. We also call this the calcium phosphate or simply phosphate mineral family, as all of the minerals contain calcium and phosphate, PO4, in addition to other elements. Your bone primarily consists of collagen. Collagen is not a mineral. It's a fibrous protein that makes up living, growing bone tissue, a framework. Your body adds apatite minerals to this framework to add strength and to harden it. Suffice it to say that minerals are an important part of who you are. You need minerals. Recall that minerals are solid, naturally occurring compounds, and that each mineral has a unique species name, chemical formula, and crystalline lattice structure. The compound described by the chemical formula repeats itself over and over again throughout the mineral structure. The study of minerals is called mineralogy. So far, mineralogists have discovered over 2,000 mineral species, and they continue to report more species every year. These thousands of minerals display a wide range of observable properties, such as crystal color, geometry, and hardness. Diamond is the hardest mineral on Earth, even though it consists of only one element, carbon. The hardness of each other mineral on our planet is defined with respect to diamond. We can measure mineral hardness, the ability of a mineral to resist being scratched, by using an instrument called a sclerometer. This instrument, in essence, measures the width of a scratch made by a diamond. Although sclerometers are very useful, geologists tend to report and measure mineral hardness using something called the Mohs scale of mineral hardness. It's a qualitative ordinal scale, meaning that the values on the scale are not measured, but instead are an indication of where a mineral ranks in terms of hardness. Diamond, not surprisingly, is located at the top of the scale. Talc, the softest mineral, occurs at the other extreme end of the scale. Talc is so soft that you can scratch it with your fingernail. What are the most common minerals in sedimentary geology? The answer depends on where you look. Let's start our discussion with bridgemanite. Bridgemanite is probably the most abundant mineral on Earth. I say probably because we cannot know for certain. In fact, the only accessible source of bridgemanite on Earth is meteorites, space rocks like this one, which have been floating around our solar system ever since its origin. Most meteorites were produced from material left over from the formation of the planets. For this reason, meteorite minerals provide clues about the processes involved in the formation of the planets, including Earth. These clues suggest that bridgmanite may be one of the most abundant and common minerals that exist under the high temperatures and pressures of Earth's mantle. Roughly 80% of the mantle on Earth may be bridgmanite. Because the mantle is hundreds of miles thick and the crust is very thin, one can safely assume that bridgmanite is the most common mineral on Earth. Regardless, sedimentary geology is focused on Earth's thin outer crust, not the mantle, and there is no bridgmanite in the crust that we know of. So even if bridgmanite is the most abundant mineral on Earth, it is actually one of the least important for sedimentology and stratigraphy. So then, what are the most common and most important minerals in the crust? We know a lot about the minerals that make up the crust. The most common minerals in the Earth's thin outer crust are feldspars and quartz. Feldspars are the principal components of most rocks. Like apatite, they make up an entire mineral family. All of the minerals tend to have elongate crystals made of silicon, oxygen, and aluminum, along with varying amounts of potassium, sodium, and calcium. There are 3 end members in the family: potassium, sodium, and calcium feldspars. Potassium, or K feldspars, are the most common. They are also known as potash feldspars. K feldspars are the most common grains in sedimentary rocks. Of them, orthoclase is the most common mineral. It forms from the cooling of magma and makes up igneous rocks like granite. When these rocks are weathered and eroded to produce sediment, the orthoclase can become grains of sedimentary rocks like sandstone. Another K feldspar mineral, known as microcline, has the same chemical composition as orthoclase, but it has an entirely different crystal lattice structure. So they are considered different minerals. Like orthoclase, microcline forms from the cooling of magma, makes up igneous rocks like granite, and can be found in sedimentary rocks like sandstone. Microcline, however, is less common than orthoclase. Sodium and calcium feldspars are known as plagioclases. Plagioclases are common on Earth and the Moon, and they may actually be the most common minerals on Mars. The sodium end member is known as albite, and the calcium end member is known as anthrite. Albite is common, but anthrite is rare on Earth. It is, interestingly enough, common on the Moon. Regardless, both come from igneous rocks. In addition to these feldspars, the other most common mineral in the crust is quartz. Quartz consists of silicon dioxide, which is also known as silica. As these names suggest, quartz consists of repeated units of 1 silicon atom and 2 oxygen atoms. Quartz is a major component of many sands, silts, sandstones, and siltstones. It is not surprising then to learn that glass and mirrors consist of silica, as those things are made from superheated sand. But why are quartz and feldspars the most common elements in the Earth's crust? The answer is complex, but it boils down to two main reasons. For the first reason, we have to go back, all the way back to the beginning, to the formation of our planet. The Earth formed from material left over from the creation of our Sun. This space dust orbited the Sun just as the planets do today, and over the course of geologic time, the dust began to collide, aggregate, and coalesce under the influence of gravity. Under these conditions, where there was many high-pressure collisions, the dust began to heat up, and from it emerged a hot molten mass of material, which would ultimately become our planet. As the molten material began to cool, heavy elements like iron and nickel sank under the influence of gravity to the center of the planet, where they now make up the Earth's core. Lighter elements like silicon and oxygen were displaced to the surface of the planet, where they now occur in the quartz and feldspar minerals of the crust. The other reason that quartz and feldspar are probably common in the crust is because that they are hard minerals. At the very least, they are harder than many of the other minerals found in the crust, like calcite. Because these minerals are so hard, they aren't so easily destroyed. They are made to last. But the crust contains many other minerals besides quartz and feldspars. Which ones are most important, you ask? The answer depends on who you talk to. Here are the ones that matter most to me. Calcite and aragonite are important, not just for Earth history, but for understanding life on our planet today. These minerals make up a calcium carbonate mineral family. In both calcite and aragonite, the basic unit consists of 1 calcium, 1 carbon, and 3 oxygen atoms. They are identical in composition. Although calcite and aragonite are identical in composition, they have different crystal lattice structures. This is an important distinction, as it affects not just their observable properties, but also their stability. Aragonite is considerably less stable than calcite. Over geologic time, we see that aragonite is naturally converted into calcite. This phenomenon helps to explain why calcite is so common in the Earth's crust and why aragonite is so rare. Most of the aragonite on Earth has been transformed into calcite over time. Limestone, a type of sedimentary rock that is widespread in the geologic record, consists mainly or entirely of calcite. Perhaps more importantly, calcite and aragonite are the most common minerals found in fossils. Students are often surprised to learn that the most common fossils are not dinosaurs or anything else that lived on land. The most common fossils are seashells because they are common, abundant, and stand the best chance to be fossilized. Calcite and aragonite serve the same purpose that apatite serves in bone. The marine organisms use calcium carbonate to strengthen and harden their tissues. Indeed, calcite and aragonite are the most common minerals for marine animals that produce shells. Clams, bivalves, gastropods, snails, and coral all produce hard shells made of calcium carbonate. Coral, in particular, are heavy biomineralizers. They build absolutely massive reefs made of calcium carbonate. That said, calcite and aragonite are relatively soft minerals. You can scratch them with pennies, knives, and even pieces of feldspar and quartz. There are some other minerals that you should know because they are similar to calcite and aragonite. They are called dolomite and siderite. Altogether, calcite, aragonite, dolomite, and siderite make up a carbonate mineral family. Dolomite has a different chemical composition than calcite and aragonite. It consists of one calcium, one magnesium, and two carbonate molecules. Dolostone is a sedimentary rock that consists mostly or entirely of the mineral dolomite. Limestones and dolostones are both considered carbonate rocks, as they consist of minerals containing the carbonate anion, CO3. In fact, calcite and dolomite have fairly similar properties and can be difficult to distinguish based on sight alone. Siderite does not have calcium or magnesium. It is an iron carbonate mineral that is commonly found as cement inside sedimentary rock. Notably, siderite has the same crystal lattice structure, but a different chemical composition than calcite. For this reason, it can be very difficult to distinguish calcium and iron carbonate minerals by sight alone. A chemical analysis or reaction of some kind is typically required. Fortunately, there is an easy way to distinguish calcite and aragonite from dolomite and siderite. We use this method to distinguish between limestone and dolostone as well. To identify and distinguish these minerals and rocks, geologists employ what is called the acid test. The test is very simple. Simply drop a little hydrochloric acid on a sample. If the sample fizzes, then it means that there was a reaction that produced a gas, carbon dioxide. Therefore, the sample must contain calcite or aragonite or dolomite. If the sample is a rock, it therefore must be limestone or dolostone. You can usually go one step further for rocks as well. Limestone tends to be more reactive on the surface than dolostone. So if there is a lot of fizzing, then you can safely conclude that the rock is probably limestone. If there is no fizzing whatsoever, you can conclude that the mineral is siderite or something else entirely. The last groups of minerals which are very important to sedimentary geology are called micas and clays. They consist of silicon and oxygen plus various combinations of elements like potassium, aluminum, sodium, calcium, iron, and others. They tend to form in igneous and metamorphic rocks and are called sheet minerals. Their crystal structures consist of thin sheets. These sheets are very soft and delicate, so they break up easily. For this reason, micas in particular tend to break up into thin, platy flakes, which are fairly easy to identify, particularly with the aid of a microscope or hand lens. Some of the most common micas are groups known as biotite and muscovite. Whereas biotite minerals tend to be brown, muscovite minerals come in a variety of colors. They can be difficult to distinguish without the use of microscopic and X-ray analysis. Clay minerals are also sheet minerals, but the sheets are usually much smaller and less impressive. You usually can't see the sheets without the aid of advanced electron microscopes. Common examples of clay minerals include kaolinite, montmorillonite, illite, and chlorite. As we further explore methods of analyzing sedimentary rocks, you will learn more about these minerals and many others. The ability to classify and recognize them is a practical skill, which requires a great deal of training, work, and experience.